In this section, we will talk about the concept of discrete probability distributions. Let's begin just by talking about and distinguishing between the two types of distributions. We will cover discrete situations in this section. A discrete random variable, as we've already mentioned, is the idea of when you count something. And mathematically what that means is that the outcomes will be specific points along the real number lines. That means when you have these specific points, in the discrete case, how the probability will work is we'll assign probability to each outcome in the probability distribution. The other type of probability distribution, of course, is a continuous probability distribution. And this is when you measure something. So here you have an infinite number of outcomes because you have an infinite number of points between any two distinct points on the real number line. So since you can continuously break down the scale, you lose that ability to assign probability to each outcome. So we have to look at a continuous random variable differently. But in this section, we're going to focus on the discrete case, but it is important to distinguish between the discrete and the continuous case, because the way we deal with probability in the two cases is slightly different mathematically because of the nature of the variable. One has specific points that you can assign probabilities to, and continuous variables do not. The general ideas work the same, but mathematically it is different. So what is a probability distribution? Well, a probability distribution essentially identifies two things. It identifies what's all your possible x values, and then it identifies the probability for each one of those. So when we identify a probability distribution, we will typically just list out the x values. In the discrete case, we'll just list out the x values, and then we will identify the corresponding probability for each of these x values. There are some criteria that need to be satisfied in order for it to be a probability distribution, and in our case, a discrete probability distribution. I'm always going to throw this first idea out. Of course, the first thing you have to do with a probability distribution is to figure out if it's discrete or continuous, what kind of variable you're dealing with. So, of course, for it to be a discrete probability distribution, the first thing is your random variable x does have to be a discrete random variable. The other two are in terms of the probability. This one is pretty straightforward. We know this for all probability anyway. All probability has to be between 0 and 1. The smallest probability can ever be is 0. The biggest probability can ever be is 1. Anytime you calculate a probability, you should make sure it's, of course, within that interval. Otherwise, you know you made a mistake. And then the last one is kind of the one that's an important check, and it's a good thing to check when you create a probability distribution, is just make sure that the sum of the probabilities is 1, because remember, 1 is the total probability. It's an outcome always happens, so when you have all of the possible outcomes, the total probability has to be 1. So it's nice whenever you create a discrete probability distribution just to verify that those probabilities do sum to 1, otherwise it's not a valid probability distribution. So once we have these random variables, of course, one of the things that we always want to do is describe them. The most common way to describe a variable, as we talked about before, is with the mean and standard deviation, and that's what we will do here as well. There's a couple differences between what we do in the probability distribution and what we do in a data set when we take a sample. So let's talk a little bit about those as we go through the idea of the mean and standard deviation. The population mean. So the first big difference that you should notice is now we are no longer dealing with the sample. We are dealing with a population. Whenever we collected data from a sample and we described it using the mean, we used x bar as our notation. So x bar always represents the sample mean. You'll see the symbol there, that's a lowercase mu in the Greek alphabet. You say it like mu, so you say it mu. Mu is the symbol for the population mean. Most of the time in statistics, what you'll find is that we use the the Greek alphabet for population values or for parameters, and we use R alphabet for sample values or statistics. So you can see that for the mean, mu is used for the population, X bar is used for the sample. So that's the first difference. When you have a probability distribution, you actually have all of the possible X's. So that means you have your entire population along with their corresponding probabilities or likelihood. Another thing that's different with a probability distribution as compared to when we just calculated the mean before is we were assuming that our sample came from a simple random sample, meaning all the probabilities were equal. Well, whenever you look at a probability distribution, most of the time the probabilities are not all equal. So if they are all equal, you can technically just add up the X values and divide by how many you have, and that will work. But the problem is most of the time that doesn't work, because now you're going to have some X values that are more likely to occur than others. So you actually have to calculate really a weighted average, and things are really just weighted on their probability. The more likely they are to happen, that means they're going to happen more often basically in your data set. And when they happen more often in your data set, that means they need to be weighted more in terms of what a typical outcome would look like. So the population mean formula you can see there. This is not a hard thing to calculate with a discrete distribution. All you have to do is take the sum of your X times your P of X values, and that will give you your population mean. Another term that you will hear in terms of these probability distributions is the idea of an expected value. So I do want to make sure you understand that term. It's something that I will sometimes ask. Sometimes I'll say, what's the expected value of the probability distribution? So you have to know what that is. It's not hard, but the expected value is the mean of a probability distribution. So I may ask you to calculate the mean. I may also ask you what's the expected value. To get the standard deviation, of course, we have to start with the variance. So the population variance is denoted by sigma squared. Remember, the sample variance was S squared. The population is sigma squared. So that's actually a lowercase sigma that you see there. That's a lowercase sigma squared. The sum sign is actually a capital sigma in the Greek alphabet, but that lowercase sigma, that is what we use for the standard deviation, and then of course sigma squared is used for the variance. So the variance formula that you see here, the first one is the conceptual formula, and it's also really just a weighted average. If you compare that to the mean formula, you'll see that it looks very similar. The only difference is instead of having that x, you have x minus mu squared. And basically that's what you do with the variance, is you're taking the average squared distance the x values are from the mean. So you just replace that x with x minus mu squared, and it gives you the average squared distance the data points are from the mean. Now, computationally, we're not going to use that. We're going to use the second version of the formula, and here in a minute I'll show you these are algebraically equivalent. But when you go to calculate the variance with a discrete probability distribution, the best formula to use is this sum of x squared times p of x minus the mean squared. It's easiest to use when you do this by hand. Of course, the standard deviation always works the same way. Once you get the variance, you take the square root of the variance, and that will give you the standard deviation. The standard deviation is just the lowercase sigma. So just like the sample standard deviation is S, the population standard deviation is that lowercase sigma. So let's go through this population variance, and let me just go through the process of showing you that these formulas are equivalent. So we'll start with the first one, the conceptual formula that comes from the definition of variance. We'll start with that idea of the sum of x minus mu quantity squared times p of x. So let's just manipulate that and show that it's equal to the other version of the formula. So here's where you use basically your rules of sums. Of course, we're also going to have to use some algebra as we go through this process. Whenever you simplify these things, we've done this a couple times now, it's important that you kind of get the flow of it, because they are all very similar in a lot of ways. Most of the time when you're dealing with these sums algebraically, most of the time what you do first is you just simplify anything that needs simplified before you deal with the sum. And then once you do that, then what you can do is you can essentially sum each part. You can use the one property where we sum each part rather than some big expression. We sum each part. Once you sum each part, then you can deal with constants. We know that we can pull constants out in front of a sum. We also know the sum of a constant is n times that constant. And then once you do that, then it's just a matter of simplifying algebraically. And once you simplify, then you're done. And it's always really that same process. So you got to get used to that. We do that fairly regularly in class. So the first thing, of course, we have to do here is we have to square that thing out. We have to square before we sum. So the first order of operation is to square. We have x minus mu, so you just simply use FOIL, square that thing out. That gives you x squared minus 2 mu x plus mu squared. Next, we have that times p of x out there. So we also multiply before we sum. So before we deal with the sum, we need to distribute that p of x. And that's what you get here. So all we did there was distribute p of x, and we get the sum of x squared times p of x. So there's basically a p of x in every one of these terms, minus 2 mu x times p of x plus mu squared p of x. So that's just your basic simplification. So we can get it in the right form so we can start dealing with the sum. So now, as I mentioned before, we can sum each part, right? We can break this up and say, and sum that first term minus the sum of the second term plus the sum of that last term. So we're going to sum each part, and then once we sum each part, then we can start to deal with the constants. But that's the general process for these kinds of situations. Okay, so let's deal with the constants. Well, that first term is quite simple because there are no constants. Everything is in terms of x, and x is our variable. If you look at that second term, we have 2 mu x p of x. So x times p of x, that is in terms of x. The 2 mu is a constant. Do remember that the variance is based on the mean. So when you calculate the variance, you already know what the mean is. The mean is some constant. So that value of 2 mu, you can pull out in front of the sum because that's simply a constant. If you look at the last term we also have that mu squared. So if mu is a constant, so is mu squared. So we can pull that constant mu squared out front, and all we're left with is the sum of p of x. So now we're at a point where we just need to simplify. So there's a couple things you got to notice here in order to figure this out, but you'll see the first term didn't change. But notice that we're left with, in that middle term, we're left with the sum of x times p of x. Well, if you look at the formula for the mean is the sum of x times p of x. So that is nothing more than just mu. So all I did there was I just replaced that sum of x times p of x by mu because that's what it's equal to. In that last term, we're just left, in terms of our sum, we're left with the sum of the probabilities. Well, we just said that in order for it to be a valid probability distribution, the sum of the probabilities has to be equal to 1. So the sum of the probabilities there is just equal to 1. So then we can just simplify a little bit. We can combine those mu's in the middle term and write that as 2 mu squared. In that last term, it's just mu squared times 1, which is just mu squared. So then you should notice the last two terms are like terms. We have minus 2 mu squared plus mu squared. So that means we're left with minus 1 mu squared. And that gives us that computational formula that we were trying to come up with. That gives us the sum of x squared times p of x minus the mean squared. This is how we know these two things are mathematically equivalent. You can show it algebraically. It's important you're able to do this. This is a little more messy than what I would give on a test, but you should be able to manipulate a basic sum and be able to use the properties in order to simplify it algebraically. Okay, so now let's look at some examples. So I wanted to just kind of run through some of the things in the chapter, but let's get into some examples so you can see how some of this stuff works. Here's our first example. Suppose we are analyzing a basketball player's statistics and identify the following probability distribution. The random variable x is the number of free throws made on a 2-shot foul. So when they take a 2-shot foul, they're either going to make 0, 1, or 2 shots. The probability that this individual makes 0 shots is 0.2 or 20%. The probability they make 1 is 0.35. The probability they make both shots is 0.45. So we're going to be given this information. So the first thing that we're going to look at here is, suppose we want to find the mean for x. So you can see here, obviously the probabilities are not all equal. So they're going to make 2 shots more than they're going to make 1 shot or 0 shot. So that means that value of 2 needs to be weighted in the average more than those other values. So if you think about that, that tells you the mean here is going to be something, it's not going to be 2, but it's going to be something bigger than 1, right? Because it's going to be closer to 1 than it is to 0, because, it's going to be closer to 2 than it is to 0, because 2 is way more likely to happen. Okay, so to calculate the mean, we already looked at this formula. We're going to take the sum of x times p of x. So in order to do this, what we need to do is we need to first, let's just use our order of operations. We need to first multiply x times p of x, and then we're going to sum those. So this is not all that different than what we did with sums a couple sections back, where we were just calculating sums. The way you do this is you just create columns for what you need. So we need x times p of x. So let's just create a column that is x times p of x. So to get that column, we just take 0 times 0.2, that's x times p of x, and get 0. We take 1 times 0.35, that's 0.35, and we take 2 times 0.45, that's 0.9. That gives us the column of x times p of x. Now we need to sum that column, and when we sum x times p of x, we sum that column, we get 1.25, and what that tells us is that tells us our mean here is simply 1.25. That's how the calculation of the mean works. Once you have your probability distribution set up, you just create this column of x times p of x values, sum it, and that will give you your mean. Okay, let's look at the variance. So the variance formula is a little more messy. It is the sum of x squared times p of x minus the mean squared. So we're not going to worry about the minus the mean squared yet. Really, the first thing you have to do with the variance is you have to figure out that sum. So we got to figure out that sum of x squared times p of x. That's what we got to figure out first. Order of operations would tell us first we need to square our x values. And then once we square the x values, then we need to multiply those x squared values by p of x. And then we sum. So I usually create a couple columns here. I just create a list of my x squared values because that's what I need to do first. So you just square x, 0 squared 0, 1 squared is 1, 2 squared is 4. That gives you your x squareds. Then you need to take x squared times p of x. So make sure, if you lay it out like I did here, make sure you're careful and you multiply the right columns. You need to take x squared times p of x. So that means you need to take, in that first row, you need to take 0 times 0.2 and get 0. You take 1 times 0.35 and you get 0.35. And you take 4 times 0.45. So make sure you see that 0.45 under the p of x. Make sure you're looking at the right column. 4 times 0.45 gives you 1.80. And then when you sum those, you'll get the sum of x squared times p of x, which is what we want here. That works out to be 2.15. So to calculate this, once you get that 2.15, then it's very straightforward because we know the sum of x squared times p of x is 2.15. We already figured out the mean. It's 1.25, so we need to take that 2.15 minus the mean of 1.25 squared, and that will give us our variance. And you can see that our variance in this case is 0.588 if you round to 3 decimals. Standard deviation. So standard deviation is always just nothing more than the square root of the variance. So we already calculated the variance. So in this case, it's just the square root of that. So of course your standard deviation is 0.766. So given a probability distribution, this is one of the things you got to be able to do. You got to be able to go through this process of calculating the mean, variance, standard deviation. It's important that we really get a good grasp of what these things represent as we start to move into inferential statistics, which is ultimately where this discussion of probability distribution is going. Okay, let's look at another example. So here we're going to go through a longer process so we can talk about some of the different things in the section and just some different ideas of probability. In this case, the discrete random variable of interest x is the number of times a 6 is rolled when rolling a die 3 times. So we're going to roll a die 3 times and look at how many 6s we get. So in order to understand what this looks like, we're going to actually start by creating a tree diagram. So we're going to create a tree diagram for the possible outcomes, and you can identify these outcomes however you want. But it's important that you're careful when you do this. If you ever do something like this, which you really don't typically have to do this because we have some shortcut formulas that we can use instead. But if you're ever doing this, you got to be really careful, because what you don't want to do is you don't want to consider all the possible outcomes when you roll a die 3 times. Because if you do that, then that means the first roll you have 6 options, the second roll you have 6 options, and the third roll you have 6 options. So that means you have 6 times 6 times 6, or 216 total possible outcomes. So if you try to draw a tree diagram with 216 outcomes, that is going to be a mess of a diagram. But in this case, we're not really interested in all the outcomes when we roll a die. We're really only interested in 2, right? We're only interested in either we get a 6 or we don't get a 6. That's really all we care about, is we get a 6 or we don't. So if you create the tree diagram in that way, then you'll notice there's only 2 possible outcomes for each roll, which means there's only a total of 8 possible outcomes. I'm just going to use a 6 for rolling a 6 and an N for not rolling a 6. So if you create a tree diagram, it looks like this. And you can see there are 8 possible outcomes in that diagram. Of course, the first roll you get a 6 or an N, and then on each of the remaining rolls you get either a 6 or not a 6. The N stands for not a 6. From this tree diagram, we can list out the possible outcomes. So the possible outcomes look like this. Well, the first outcome is that we get all 3 6s. The second outcome is that we get a 6, and then not a 6. The third outcome is that we get a 6, not a 6, and a 6. And you can see there are 8 possible outcomes here. So that's just simply the outcomes in terms of getting a 6 or not when we roll the die 3 times. The next thing we're going to look at is we're going to look at the probability for each of these outcomes in the tree diagram. So we're going to calculate the probability for each of these outcomes in the tree diagram. So this is a little neater and a little cleaner. So here we just have those outcomes that we had listed from the tree diagram. So the first outcome is that we get 3 6s. The second outcome is that we get a 6, not a 6, and so on. But we have those outcomes listed here. So now let's think about the probability. So this is another place you have to be careful. There are 8 possible outcomes, but the probability of getting 3 6s is not 1 out of 8. And that is because these outcomes are not equally likely. You are not equally likely to get a 6 and not a 6, because the probability that you get a 6 when you roll a die is 1 out of 6. The probability you don't get a 6 is 5 out of 6. So those are not equal. So we can't just take 1 out of 8 for each of these probabilities. So this is where you use the multiplication rule. It's one of the applications of the multiplication rule, which you've already seen. So the probability of getting 3 6s is actually the probability that you get a 6 on the first roll is 1/6. The probability you get a 6 on the second roll is also 1/6. The probability on the third roll is 1/6. So we actually get 1/6 times 1/6 times 1/6, which is, if you multiply that out, that's 1 over 216. That is actually your probability. So I already have these all done. You can see them here. You can see the probability of getting 3 6s is just 1/6 for each one. You get 1 over 216. If you want to get a 6, not a 6, then that's 1/6 times 1/6. Not a 6 is 5/6. That'll give you a probability of 5 over 216. And so on. You can see all these probabilities. Each one of these, we just simply use the multiplication rule take the probability for each operation, and then we multiply those together, and that will give us, by the multiplication rule, that will give us the probability that they all occur. So in a case like this where the probabilities are not equal, you really have to use the multiplication rule. So the next thing we're going to do is we're going to use this information to actually talk about x, because we haven't done that, and that's really the whole point of this problem. But you can see, in order to get to x, you really have to, if you do this the long way, you really have to go through this big long process of figuring out what all the possible outcomes are when you roll a die 3 times, and then you have to figure out what the probability is for each one. So x, the random variable of interest, what we're really interested in here is x will be the number of 6s that I get when I roll the die 3 times. So if you roll a die 3 times, then you can get either 0 6s, 1 6, 2, or 3, right? So those are your possible outcomes for x. And then each one of those has a corresponding probability. I have those laid out here. So you can see the probability that you get 0 6s. So x is the number of 6s I get when I roll the die 3 times. I'm going to get 0, 1, 2, or 3 6s. So whenever x is 0, that's saying what's the probability that I get 0 6s. So if you look at that list of outcomes to the left, you can see where we get 0 6s is n. It's that bottom outcome. That has a probability of 125 over 216. So all I'm doing is pulling those numbers. The probability that I get 1 6. Well, there's actually more than one way to do this, because it could be the first outcome that is a 6, it could be the second outcome that's a 6, or it could be the third outcome that's a 6. So if you look through these, you'll see that there are 3 different ways to get 1 6. You'll see that you could get 6n, you could get n6n, or you could get n6. If you look at all those probabilities, they are all 25 over 216, which means the probability of getting 1 6, it can happen 3 different ways, each one with a probability of 25 over 216, which gives you a total probability of 75 over 216. Getting 2 6s works the same way, because that means you're getting 2 6s and one that's not a 6. There's 3 different ways that can happen. That's really where that number 3 comes from, but you can see that from the list that there are 3 ways to get 2 6s. Each one of those has a probability of 5 over 216. That will give you a probability of x being 2 of 15 over 216. Getting 3 6s, that's that first outcome where we have 3 6s. We already know that probability is 1 over 216. So this is my probability distribution. When we talk about a probability distribution, that's what we're talking about. We're talking about what are the possible x values, and then what's the probability for each one. Now I'm going to clean it up a little bit and just give you the x's and the probabilities. And when you do that, this is what it looks like. The probability x is 0 is 125 over 216. The probability x is 1 is 75 over 216. The probability x is 2 is 15 over 216. And the probability x is 3 is 1 over 216. So now we have our probability distribution. A good thing to check, and we mentioned this earlier, is to just verify that it's valid. Make sure you haven't made any mistakes. So, the 3 things that we talked about. Is the random variable discrete? Yes. 0, 1, 2, 3. That is countable. Those outcomes are specific points along the real number line. That is a discrete random variable. Are all the probabilities between 0 and 1? And of course, if you go through those P of x values, you see that they're all between 0 and 1. And then the last one is a good thing to check, because lots of times if you make a mistake, you'll find it when you do this. And that is the sum of the probabilities must be equal to 1. So if you add those, they all have the same denominator, so I'm just going to add the numerators. We get 125 plus 75 is 200, plus 15 is 215, plus 1 is 216, so that gives us 216 over 216. The sum of those probabilities is equal to 1, which means we satisfy the criteria. This is a valid probability distribution, and we can be very confident that we did not make any mistakes. So now that we have the probability distribution, we can do what we did before. We can calculate the mean, and that's what we are going to do here. So to calculate the mean, we first need to create this column. This is the way I always do it, at least. It's how we typically deal with sums. We just create columns for what we need. We know the mean is the sum of x times p of x, so just create that list of x times p of x values. We get 0 times 125 over 216 is 0. 1 times 75 over 216 is 75 over 216, and so on. You can see the math there. And when we sum those, we get 108 over 216. So that gives us a mean here of 0.5. If you think about this mean, it actually makes a lot of sense. If you think about it, and you roll the die 6 times, you would expect to get a 6 on average 1 out of every 6 times, right? So if you rolled it 6 times, you would expect the mean to be 1. That means if you roll the die 3 times, you would expect the mean to be a half. That's essentially the way this works. We had to go through a lot of work to figure that out, at least using this method. But the mean in this case is 0.5. And if you really think about it, it does make a lot of sense why it would be that value of 0.5. Standard deviation. So standard deviation, of course, is a little more work. We need to figure out that sum of x squared times p of x quantity. So again, we need to create columns so that we can do that. Like I said earlier, I recommend that you just list out your x squared value. So you just take each x and square it. And then you take x squared times p of x. Make sure you multiply the correct columns. Here you would get 0 times 125 over 216. That's 0. 1 times 75 over 216. That's 75 over 216. 4 times 15 over 216, that gives you the 60 over 216. And 9 times 1 over 216, that gives you the 9 over 216. So you see that column of x squared times p of x values. And then we're going to sum that column. If you sum that column, you will get 144 over 216. So that's what we need for the variance formula. So now we have everything we need for the formula, and you can see I plugged it in there. The variance. You got to get variance before you get standard deviation, because standard deviation is just the square root of the variance. But the variance here is that sum of x squared times p of x is 144 over 216. Remember, we just calculated the mean. It was 0.5. So you subtract 0.5 squared. That will give you your variance. So your variance here, when you work it out, works out to be 0.417. So now to get standard deviation, you simply just take the square root of that variance, and the square root of that variance will give you the standard deviation, which is 0.645. So do keep in mind, if you're ever asked for standard deviation, the process to get standard deviation is first you must calculate the variance, then from that you take the square root. That will give you the standard deviation. There's one other thing we're going to do with this problem is talk a little bit about the binomial distribution. So of course I set this up. This actually is a binomial distribution, which is what we're going to check here first. Is this a binomial distribution? So there are lots of discrete distributions. And what statisticians have done over time is they've come up with distributions that have common characteristics. And there's lots of different ones, and there's these different specific types of discrete probability distributions have certain characteristics. And once you know those characteristics, then you can use basically these shortcut formulas in order to find things like probability, mean, and standard deviation. So in this class, we don't go through all the, there would be a bunch of them, but we don't even go through a bunch of these different kinds of specific discrete probability distributions. But I do want you to be aware that if you know you have some specific characteristics within a distribution, then sometimes those characteristics will lead to shortcut formulas. And the binomial is what we use in order to illustrate that idea. So the criteria for the binomial distribution. The first thing is the experiment must consist of n identical independent trials. So binomial experiments are when you do the same thing over and over and over again. So in this case, notice, what are we doing? We are rolling the die 3 times, right? So we are doing the same thing 3 times. That means there are 3 identical and independent trials. So identical means you're doing the same thing. Independent means what it means improbability. It means what I do on the first roll is not going to affect what I get on the second roll, which we know to be true. When I roll the die once, it's not going to affect what I get when I roll it a second time. So these are 3 identical independent trials, so we satisfy that characteristic for the binomial. The second characteristic is each trial must result in one of 2 outcomes, and we call these outcomes a success and a failure, which we'll denote by S and F. So in lots of experiments, we actually define what S and F is. A success is typically what you're interested in, and a failure is what you're not interested in. So in this case, we're interested in rolling a 6. So we're simply going to let getting a 6 be a success and not getting a 6 be a failure. So notice we do have 2 outcomes here for each trial. We're either going to get a success, which is a 6, or not a success, which is not a 6. The probability of success, and this is more of a notation thing than anything, the probability of success we always call P. So P in this case is going to be that we get a 6, it's going to be 1/6. The probability of a failure is Q, that's probably we don't get a 6, so in this case that will be 5 out of 6. This must be true for all trials. Of course, P and Q are complements of each other. Another way to get Q is just take 1 minus P. 1 minus 1/6 gives you 5/6. And this must be true for all trials, which only makes sense. You're doing the same thing and they're independent trials, so of course the probability is going to be the same for each trial. And then the last criteria is just what you're interested in. The way the binomial works is it's a scenario where you're interested in how many successes you are going to get in the end trials. So we've already said in our scenario we have 3 trials. A success is that we get a 6. So in our case, we're interested in how many 6s or how many successes we get in those 3 trials. So that means we've satisfied all the criteria for the binomial. So yes, this is a binomial. It is a binomial with 3 trials, a probability of a success or P of 1/6, and a probability of a failure of 5/6. Okay, so now that we've established that, let's go through some of the things, or let's go through calculating probability, calculating mean, calculate standard deviation for a binomial experiment. So we've actually already done these. We did this through the process of the tree diagram. So as we go through, it's important that you recognize that these probabilities are going to be something that you've seen before, but it'll also illustrate to you how the binomial formula works. So this is the binomial probability formula. If you want to find the probability that x equals some specific value, then you use this formula, which is n factorial over x factorial n minus x factorial. That part of the formula actually tells you how many ways there are for this to occur. So like in this case, we're interested in getting x being 2. So that means that part of the formula will tell you how many ways there are to get 2 6s and 1 that's not a 6. P is, of course, the probability of success. You take that to the x power because that's how many of those 1/6 you're going to end up with when you do that multiplication rule. And then Q is the probability of failure to the n minus x, and that will give you the number of n's, basically the number of outcomes that are not a 6. It'll give you that within the multiplication rule. So hopefully that made sense. So in this case, if we plug in what we know that n is 3, so we get 3 factorial. We're finding the probability that x equals 2. That's 2 factorial, 3 minus 2 factorial. Well, when you work that out, you get the 3 minus 2 factorial is just 1 factorial, so that really just goes away because that just becomes 1. So you're left with 3 factorial over 2 factorial. That just becomes 3, which is why you see that 3 over there. Then we have 1/6 to the second power times 5/6 to the first power, or 3 minus 2 power. So when you multiply that out, you get 1 squared, which is 1, times 5 to the first, which is 5. So you get a numerator of 5 over there. And then we get 6 squared in the denominator and 6 to the first in the denominator. So that's 6 to the third power, which is 216. And what you end up with is 3. That's how many ways there are for this to occur. Times 5 over 216. That's the probability for each of these outcomes. And that gives you a total probability of 15 over 216, and that should look familiar to you. Whenever we created this probability distribution before from the tree diagram, the probability that x was 2 was 15 over 216. That gives you a probability when you write it out as a probability of 0.069. So this is a shortcut formula that will do the same thing for you as going through that big long process of the tree diagram and then figuring out the probability distribution, getting all the probabilities, and then calculating the mean, calculating the standard deviation. There's shortcuts for all those things if you know that it's a binomial and you recognize that. So not all discrete distributions are a binomial. This only works if your distribution is a binomial. But if it's a binomial and it satisfies those characteristics, then you can use these shortcuts. Probability of x equals 3, and this works exactly the same way, so I'm not going to spend a lot of time explaining it, but you can see basically everywhere there is an x instead of there being a 2, now there's a 3. The way that works is in that first part there where you have the factorials, you get 3 minus 3 factorial, which is 0 factorial. Don't forget that is 1, so that just goes away. So you're left with 3 factorial over 3 factorial, which is 1. There's only one way to get 3 sixes when you roll a die, so that probability is 1. And then if you look there, you get 5 6 to the 0th power, so that also just goes away because that's 5 6 to the 0th power is just 1. So all you're really left with here is 1 6 to the 3rd power, which is 1 over 216. And of course, that's the probability that we calculated before as well. That'll give you, if you write it out as a decimal, 0.005. Another thing that you will sometimes see with these is inequalities. So it is important with inequalities not to just use the formula. For example, if it says the probability that x is greater than or equal to 2. So if x is greater than or equal to 2, that means you could get 2 6s or you could get 3 6s. Those are the only possibilities, greater than or equal to 2. So in order to do inequalities, you have to do each one of those, which we've already done them here. So you would take the probability of x equals 2 plus the probability of x equals 3. Add those together, and that would give you the total probability that x was greater than or equal to 2. So anytime you have inequalities, you've got to calculate the individual probabilities and then use those in order to get the probability that you want. The mean. So the mean of a binomial is actually pretty straightforward. It's got a nice shortcut formula. To find the mean of the binomial, all you have to do is take n times p, and that is it. So if you know it's a binomial, and in this case we know n is 3 and p is 1/6, you can just take that n times p, or in this case that 3 times 1/6, that'll give us a mean of 0.5. Notice how much quicker that is than how we calculated the mean for this distribution before. If you remember before, we also got a mean of 0.5, but it took way more work than just taking 3 times 1/6 to get that mean. Again, this is the benefit of knowing that we have a binomial distribution. We can use these shortcuts. The variance is also very straightforward in a binomial distribution. The variance of a binomial distribution is just n times p times q. So in this case, that would be 3 times 1/6 times 5/6. If you work that out, you will get 15 over 36. That will give you 0.417. And again, if you compare that to what we did before, you will see that it is exactly the same as when we went through that process of creating this probability distribution from the tree diagram and then using that sum of x squared times p of x minus the mean squared formula in order to get the variance. The nice thing about those previous formulas, though, is they work for any probability, any discrete probability distribution. These formulas here only work if you know your distribution is a binomial. Standard deviation, of course. The standard deviation is just the square root of that variance. So the standard deviation here is 0.645. And that is, again, the same as the value that we had before. So there's a lot of important stuff in this section. It is a little more mathematical, which kind of happens as we move throughout the semester. Things do get more mathematical. The big things in this section, of course, is understanding what a probability distribution is, how to set up a basic probability distribution. Understanding how to figure out the mean and standard deviation for any discrete probability distribution when you have that probability distribution given to you or when you figure it out. And then you need to be able to deal with these situations where we have a binomial experiment. In some binomial experiments, you would never want to create the tree diagram, because if you have 100 trials, it would be a nightmare to create a tree diagram with 100 trials. But we can still use these shortcut formulas to find probabilities even when we have a lot of trials, or even when something would be really messy if we did it using kind of the old school method of creating the tree diagram and the probability distribution. We could do it that way, but some of these problems could become a real nightmare trying to do them that way. So these shortcut formulas with the binomial are important. You got to be able to recognize when something is a binomial. I try to be nice about that whenever I ask you questions and say, you have this binomial experiment. So when you know it's a binomial experiment, then you know you can use these shortcuts for the binomial. This idea of probability distributions is really important because we're going to continue talking about it. And when we get to inferential statistics, the way we control probability of error in inferential statistics is really based on this underlying idea of the sampling distribution, which is a probability distribution that allows us to control that error. So anyway, that is the end of this section, the end of section 5.